So this talk is about scalable ML pipelines, in particular using Dask, and we'll go through a few design patterns that we have found to be useful in our work. Before we get started, a big thanks to Anaconda, first of all, for hosting a great conference so far. We have enjoyed it so far very much, networking and learning from others. So to introduce ourselves, I am Rajendra, co-founder of Manifold, and Jason is an ML engineer at Manifold. And I know we are just after lunch here, and it can be tricky, but we'll try to keep you awake as much as possible. All right. So with that, few words about our company. Manifold is we are a consulting firm basically focusing on data engineering and machine learning. So we build data pipelines and machine learning pipelines for our clients. We also maintain them. Okay, so a few words about audience and a couple of logistics here. Can I have a quick show of hands? How many of you are familiar with Dask? Okay, how many of you use Dask in ML pipelines in the context of machine learning? Okay, cool. That tells me where to focus for the talk. So I think most of you should be okay because I saw a lot of hands going up. As long as you can follow the high-level points, it should be okay. The details you can always follow in the notebook that we shared here. It's on GitHub. And the slides are also available there at that link. I'll pop the slides link again at the end, so you have time to get them. And quickly about agenda for the talk. I'll spend maybe about 8 minutes talking about introduction and motivation, why we should even consider Dask in machine learning pipelines. And we'll spend bulk of the time on design patterns, simple design patterns that we have found to be very effective in ML pipelines, and then maybe 5 minutes on conclusion and wrapping up the main takeaways. So with that, why even consider Dask? So this is a diagram of our typical process in client engagements. When we start a project, we start at the top. Understand here means both business understanding and data understanding. Business understanding is largely about finding out the goals. What is the business actually looking for? Understanding the problem. And then that quickly leads into data understanding, which is largely about what is available, how is the data looking, and how much of it is there. So this often happens within few weeks. And then we quickly move on to engineering and modeling. Engineering here refers to building data pipelines, transformations. Also, modeling means building a very simple V0 version of our model. And we try to get feedback very quickly from clients to make sure we're on the right track and everybody involved is on the same page. And in most cases, we even deploy the very simple model, the V0 version. So having this end-to-end system, although a very simple system, in place has been very effective. It gets everyone aligned towards the goal. And really after that, majority of the work is making iterations around this loop, making incremental changes. Maybe you add a new data source or a new feature and want to see the impact on the model and performance. So basically, it's this quick iteration. That's what Dask really helps with. And we're going to dive into the details how that can be done. I'll give you seconds here. But so this is a very common thing I have encountered personally, maybe not in training per se, but there's lots of stages in an ML pipeline where this comes into play. And I don't think this is only true for deep learning. the broader machine learning problems also face the same problem, from ETL to feature engineering. And really, what we are saying here is it legitimate to slack off anymore by saying, hey, ETL is running or my model is training. And it goes beyond developer productivity. And this is a cartoon. It's not entirely true. And most people, I think, actually try to do something productive while a job is running. But another key thing to consider is performance in a very holistic sense. So not just model performance, but overall your system performance is directly proportional to the number of iterations you can make to your project, right? And the number of iterations you can make through this loop is directly proportional to the speed with which you can make changes and iterate through the loop. So making a change and quickly running that change through your pipeline and observing the effect has been key. So very quickly, let's look at what a typical ML workflow looks like, abstracting away a lot of details. In general, real-world ML problems have these 4 stages. Data is often not very clean. You have to pre-process. There's feature engineering after that, which is where a lot of business knowledge comes in, domain expertise comes in, and then you model and deploy. So now, diving a bit deeper, so we have this pipeline, and what kind of operations happen at different stages of this pipeline? And to answer that question, you have to look at the data types, because the operations at different stages depend on the data, the type of data that is flowing through the pipeline. So, for example, in the pre-processing stage, if you look at text, the second one here, a very common operation is tokenization. You take large number of documents and text data you want to tokenize, which is to say extract words out of it, and then you want to clean it, remove the punctuation maybe. Similarly, time series data sets, that's the last one. It's often they have missing data in real world, and you may have to interpolate before you can process it further down the pipeline. And at the feature engineering stage, there's also a few common operations that you can see depending on the data type. For example, bag of words and TF-IDF representation is typical for text. So going further down, so you see model building. So once your data is organized and you have the features you want, that's what the data set here represents. The right-hand side of the picture is about modeling. So you choose a technique and then you train, you deploy. And the key thing is at any stage, there may be several opportunities to use Dask because you can find lots of data parallel operations. So which is to say, you can take a unit of data, apply an operation to it, and then use Dask to parallelize that operation over many units of data like that. So that's kind of the key mental model. And we have been able to use Dask in almost every block of this diagram. So for text, which we will see today as a case study, time series problems as well to compute frequency domain features, for example. So this is a mental model, kind of almost a taxonomy to keep in mind. And now, with that kind of high-level intro, we're moving into the case study here, which is about an NLP problem. This is a little bit different from what you may have seen in the talk abstract. We mentioned something about songs, but because we wanted to share the code, we picked a public data set which we can share with you. This is an ARXIV NLP problem. It is basically a data set of journal papers. So we'll use that case study to walk through that pipeline from the beginning to the end, from pre-processing all the way to the modeling end, and look at few ways we have used Dask in that example. And Jason will walk you through the pre-processing and feature engineering.
As Rajendra mentioned, we're going to focus on the arXiv repository of ePrints. And our case study is a natural language processing problem where we want to create an automatic document classifier to classify these ePrints into one of many categories. But what do we mean by this? Here's an example document, the world as evolving information. Currently, this document's hand-labeled into 3 categories: math, computer science, and quantitative biology. But what if we could automate this process and process the document and automatically label it into each of these categories? Well, arXiv is an enormous repository of over 1.5 million documents. We've downloaded about 250,000 from 5 years of data and stored them in JSON files. These documents are each labeled into one or more of the categories on the right. And as you can see, we're dealing with a relatively large amount of text data. So this is actually a really good use case where Dask can help us iterate through our loop more quickly. So the first step is pre-processing, as Rajendra mentioned. Our raw data looks something like the table on the left, with a full text abstract and a list of categories for each document. In order to prepare our data for feature engineering and eventually modeling, there's 2 operations we want to perform on this data. First, we want to tokenize the full text abstracts from one big string into a list where each element is a word. The other operation is to convert the raw category list into what's called a one-hot encoding, which is a series of columns which indicate whether or not the document is labeled as part of that category. So for example, the top paper is a math paper, but it's not categorized as any of the other categories. The bottom paper, which is the one we showed before, is actually listed in 3 categories: math, CS, and quantitative biology. So we're going to show some code in this talk, and this may be one of only a handful where you'll see code, but we'll keep it simple, highlight the important pieces, and if you want to dive deeper, you can follow in the notebook listed here and on the first slide of the talk. So our approach for writing Dask code for ML is to start small and build out this parallelized code incrementally. So first, we just want to write code in regular Python, which can process one JSON file, and then later we'll parallelize. So this code is basically just, once we read in our JSON file into a pandas data frame, we use a one-hot encoding to create our process DF, and then we'll take the raw data frame's abstract column and use pandas map functionality to tokenize every abstract in the raw pandas data frame. And we'll assign this to the process data frame as our tokenized abstract. Finally, we write this to file. So this function reads in one raw JSON file and writes out one pre-processed JSON file. Now we're ready to parallelize over files using Dask. So let's say we have some list of input files. We can use a structure called DASBag, or DB for short. It's from sequence, just loads the input files into the DASBag. And then, again, we use a similar functionality, but this is Dask implementation of map, which just calls the pre-process input JSON function on every JSON file in our list of input files. Finally, once we're ready, we call .compute, and all of these files will be processed in parallel. So this Dask preprocess function reads in all of our JSON files, processes them, and writes them out in parallel. This leads us to our first design pattern, which is to build incrementally. So writing parallelized code can be time-consuming, and in the end, we're aiming to reduce compute time, which will help us iterate more rapidly later on. But another critical consideration is to spend development time wisely. So our process is as follows. Write code to process 1 unit of work in Python. Then use Dask to parallelize over all units. In particular, DASBag and Dask delayed can be really useful for this kind of design pattern. So building incrementally allows us to move through this lean AI loop very rapidly and iterate on our models to efficiently build incremental value for our work. The next step in our pipeline is feature engineering. So now that we have our set of pre-processed JSON files, we want to build these numerical features that our model can use downstream. Something like this document matrix on the right. But there's a few intermediate steps in achieving this. So we need to first build what's called a global dictionary of all the words in all of our documents. So this is an exhaustive set of every word in every document. An example of this is the column names in the bag of words representation image. It is puppy, cat, pen, a, this is an example dictionary. But then once we have our dictionary, we can create a bag of words representation, which is simply the count of each word in the dictionary in each document. So this is called term frequency. To give you an example, look at the fourth document. That is a dog, and this is a pen. So the words is and a appear twice. Pen and this appear once. And there are no other words in this document that are in the dictionary. So those are all labeled as 0. Once we are at this stage, the next step is to use what's called a TF-IDF model. I'm not going to get into details about this, but the key here is to convert this bag of words representation into a sparse matrix that we can use in our modeling. So the way you can think of this is like each row is a document, and each column is a word in our dictionary. And the elements are some normalized frequency of the words in the document, also across documents. So to summarize, this feature engineering step is going to convert our 9 preprocessed JSON files into a document matrix ready for modeling. So implementing our feature engineering phase in Dask is as follows. First, we just want to build our global dictionary. And for brevity, I've left out the details. It's a similar design pattern as before using Daskbag. Then we have a DDF, or Dask data frame structure, which we've read in every single preprocessed JSON file into. And then we're grabbing the tokenized abstract column and using Dask apply function to apply our dictionary's doc to bow, or document to bag of words operation in parallel once we call .compute. Finally, once we have our corpus, or our bag of words representation, we can use this other library for NLP called Gensim, which computes the TF-IDF document vectors and converts it to the sparse matrix in the form we need for modeling. So the real takeaway here is that Dask data frame has an API that mirrors pandas and allows for ease of use for parallelizing over partitions, which I'll explain in just a moment. So our second design pattern is to identify the parallelizable unit of work. In our pre-processing step, this was quite natural. We had JSON files already laid out, and we could pre-process each JSON file in parallel, reading them in and writing them out to intermediate storage. But there are other use cases in tabular and time series data where we may need to think a little bit more critically about how to identify the appropriate parallelizable unit. So let's give an example. Let's say we're an e-commerce company, and we have a bunch of customer data about how they interact with our website. Customers 0, 1, and 2, maybe varying amounts of data per customer even. It may be very natural and makes sense to partition or group the data and assign them to workers according to these customer IDs. And once we've done this, we can, again, write this out to intermediate storage so that it can be easily loaded and used to perform these aggregate computations, like, let's say, the total number of times that the customer interacted with our website. So in our work, we've used this design pattern on a number of problem types, partitioning by an idea of some sort. And it's been hugely beneficial to store these intermediate results so we can load them later and iterate on features as well as for debugging. Identifying the parallelizable unit of work and storing intermediate results according to this are key aspects of minimizing compute time and therefore maximizing iterative speed. So by utilizing Dask and our design patterns to quickly iterate through our feature engineering stage, we're able to rapidly create higher quality features for our modeling and therefore higher model performance. So I'll hand it back to Rajendra to finish with modeling and conclusion.
All right. So moving on to modeling. Let's see. So this is what is called a multi-label classification problem. On the right-hand side, we have the document, a journal paper, and these are the 3 categories that are assigned to the document. And basically, we want to model and create a model or maybe a set of models that can take in the text as input and predict whether or not that text belongs to one of these categories. So one approach we can take is build a separate model for each label. So there is a model for computer science. It takes in the TF-IDF features we created as input, and it's predicting whether that journal paper should be categorized as computer science paper or not. And then there is a separate model for mathematics, and similarly others. And these are all independent models. And one thing to note here is the input is the same for all the models. It's the same TF-IDF feature matrix that's going in, except for the label. So when you train the model for the computer science model, you pass in the target variable that belongs to computer science, whether that paper is computer science or not. And for the math model, you pass in the math column. So that's the only difference, but the input, the feature matrix is the same. So maybe we can already see the opportunity for parallelizing training multiple models here. So essentially, each model is taking in the same features, a different target variable, and we want to train all of them. Instead of training one model at a time in a serial loop, we can train all of them simultaneously. So in order to do that, one thing we can do is send data. In this case, data is our TF-IDF feature matrix. We can send that to all the workers, have it available, and when it is there, we can start training our model, one model on each worker. So the first worker here maybe is building a math model. It's predicting a binary classifier, whether that journal is a math paper or not. So when the training is done, you have a set of trained models all available, and they are all trained simultaneously on different workers. So how does this look in code? So the highlighted piece here is showing the scatter part, sending the data to all the workers. So we are sending the training data, that is the xtrain, and the validation data set as well, that is the xval. And what we get back is an object called futures. It's basically like a pointer to the data that's on the worker. And while Dask is moving the data there to all the workers, we can submit this task. So basically, the important piece here is client.submit that you see. And the first argument is the function you want to execute on each of the workers. And all the other arguments are the pieces, the arguments to your function, the fit predict function. So fit basically trains all the models, your binary classifiers. Predict, in this case, takes the validation data set and makes predictions. So what we get back from this call is a list of arrays. Each array are predictions for that model on the validation data set. So, and the last piece here is, so the line before submits the code and it starts executing, and Dask takes care of all the internal details, making sure, training the model when the data is available, and waiting until it is available. And the gather call at the very end blocks our client program, so this code, until the previous line returns, in which case, by that time, you have all the predictions available, all the results of the fit predict function available in your client program. So moving on, this one, maybe I'll mention very quickly. So Dask has a drop-in replacement for grid search CV. It's a very common operation in ML workflow. Scikit-learn has a grid search CV. And Dask's replacement basically allows you to train on a cluster instead of on a single node, on a single computer. And this is generally a very compute-intensive operation, so we found this to be very helpful. We've trained random forests and gradient boosting trees using this. So to wrap up the modeling section, so maybe a design pattern that we can take away is, so scatter data first, make sure it is available on the workers, and then you can send your code to workers to execute on the workers. So this is a little bit counterintuitive. So in the normal operations, for example, ETL, you load data from your database, you bring data in to wherever your code is running. This is the opposite of it. So you send data where your workers are, and then use Dask to send a function, essentially, that can execute on those workers. And so moving on to the conclusion of the talk here, so we have seen this, four stages of a typical ML pipeline. In reality, that's not exactly how it looks. So reality is somewhat like the bottom picture. If you think of throughput, the number of data points that can flow through any stage of your pipeline, as height, then different stages have different heights. Basically, your feature engineering can be very compute intensive. So the amount of time it takes to process a single data point is much longer than maybe pre-processing for that data point. So height represents throughput. Essentially, the shorter it is, the longer it takes for a data point to flow through that stage. Then basically, they start to become your bottlenecks, and your full model pipeline is only as fast as your slowest stage in the pipeline. So in this case, for example, your feature engineering block becomes a limiting factor. And this is how Dask helps to kind of remove those bottlenecks. So in some cases, you can almost anticipate where the bottlenecks are going to be and address them. In some cases, you can react as you learn about them. And that goes back to the quick iteration cycle through the process we described earlier, which is this. And this is really how it plays into our workflow. And really, in this simple example even, we found several cases where we can use Dask. From pre-processing, in feature engineering, in modeling, we train multiple models using Dask simultaneously. And that just allows you to move through the loop quickly, make experiments faster, and the more experiments you can make, the better your overall system is going to be ultimately. So with that, I will conclude. Thank you everyone again, and that's the link to the slides. Thank you, Anaconda, again.